A former Intel CEO just walked onto a stage in Las Vegas and told the entire AI industry it built a trillion-dollar hardware bet on the wrong architecture. Not a startup founder, not an anonymous analyst. Pat Gelsinger, the man who ran Intel until December 2024, looked out at a room packed with enterprise AI leaders and said the 5 words nobody in Silicon Valley dares say out loud. GPUs suck for AI. Every data center going up right now, every rack humming at 120 kilowatts, every H100 and B200 Nvidia has ever shipped. Gelsinger says it is all built on a foundation physics itself will not let scale. And this is not a hot take. This is a technical argument about power, bandwidth, and data movement. If he is right, the entire AI hardware roadmap for the next decade needs to be torn up and rewritten. Here is the case he made. The central claim Gelsinger delivered at AI for 2026 in Las Vegas on August 4, 2026, is blunt. The dominant AI hardware path, discrete GPUs paired with high-bandwidth memory, is not just inefficient. It is architecturally wrong. Gelsinger, who stepped down from Intel on December 1, 2024, now serves as a general partner at Playground Global. The current approach, he argued, is fundamentally broken because it burns too much energy shuttling data between separate compute dies and memory stacks. Look at the public specs. Nvidia's H100 SXM draws 700 watts. The H200 lifts memory bandwidth from 3.35 to 4.8 terabytes per second. The B200 pushes roughly 1,000 watts, and a full GB200 NVL72 rack pulls about 120 kilowatts. That power budget has grown far faster than the energy efficiency of moving a single byte into arithmetic units. For large language model inference, token generation is frequently memory bandwidth bound. Weights must be read for every generated token, so even a massively parallel GPU can sit idle waiting on HBM returns. Gelsinger's core technical point cuts deep. This arrangement separates compute and memory at the wrong level. HBM stacks sit on an interposer near the GPU die, but they remain separate chips with physical distance, thermal boundaries, and interface overhead. Every movement across that interface costs picojoules per bit, and when billions of parameters are read repeatedly, those costs compound into megawatts across a data center. He argued the industry accepted GPU-plus-HBM because it was the fastest available path, not because it is optimal for matrix multiplication. AI hardware should place memory and processing closer together, reduce precision where mathematically safe, and strip out serial bottlenecks like PCIe or traditional NVLink hops. This is not a new debate. The memory wall has been documented for decades in computer architecture literature. What changed is scale. A frontier model can demand hundreds of billions of parameters, and serving it at low latency forces operators to replicate weights across many accelerators. Every copy consumes HBM capacity. Every token read consumes power. That is why hyperscalers have designed custom silicon with on-package SRAM or tightly coupled memory, and why startups have promoted language processing units that skip HBM entirely for certain inference workloads. Gelsinger's AI4 remarks gave those criticisms a high-profile platform. GPU loyalists fired back, and their counterargument is not trivial. Nvidia's CUDA platform has been built over more than a decade, and most frontier AI research is written against CUDA and its libraries. Custom accelerators may look better on paper, but often fail because the software stack is immature or they only win on narrow model sets. Nvidia has also improved generation after generation. Hopper introduced the transformer engine with FP8 precision. Blackwell moved to a dual-die design with higher bandwidth and lower energy per inference. Public MLPerf benchmark results repeatedly place NVIDIA systems at or near the top in training and inference, even as power per accelerator climbs. But here's the thing that does not automatically refute Gelsinger. A system can be the best available product and still be architecturally inefficient long-term. The real dispute is whether the industry can wait for a fundamentally different memory compute design or whether pragmatism keeps extending GPUs and HBM. Gelsinger pointed to the slowing of Dennard scaling and rising HBM costs as evidence the trajectory is unsustainable. He did not accuse Nvidia of fraud. He argued a path chosen for graphics has become an energy and cost burden for AI. That distinction matters. This is about product architecture, not misconduct. The most concrete metric he cited was energy per token. For generative AI, the relevant measure is not raw teraflops, but tokens produced per joule and joules wasted moving weights. A GPU can deliver enormous teraflops, but if most execution time is spent waiting on memory, those teraflops never convert into useful output. Gelsinger was not saying GPUs cannot run AI. He was saying they are a poorly matched engine for autoregressive inference, and the industry is paying a heavy power and cost penalty for that mismatch. The AI4 audience included enterprise AI leaders planning multi-year inference infrastructure. Gelsinger's message was practical. Do not assume the current accelerator and HBM design is the only option. Evaluate architectures by tokens per watt, not just peak floating point throughput. That framing has consequences for Nvidia, AMD, Intel, and custom silicon vendors. Hardware engineers have long criticized the memory bottleneck. GPU loyalists point to shipped products and developer lock-in. A former Intel CEO making the argument publicly shifted the debate from academic papers to boardroom strategy. What to watch next is whether Nvidia's roadmaps respond to this specific pressure. Nvidia has invested in NVLink, NVSwitch, and Grace Hopper designs, placing an ARM CPU closer to the GPU. Its disclosed Rubin platform pushes HBM4 and more aggressive co-packaging. Moves readable as partial acceptance of the memory bandwidth problem. Whether they go far enough, or whether custom architectures and optical interconnects leapfrog them, remains the open question. For now, the public record shows a former Intel chief using a keynote stage to call the industry's most successful AI hardware architecture fundamentally broken. That is a reported event grounded in measurable power, bandwidth, and data movement costs. If this breakdown hit home, smash that like button, subscribe to Tech Market Pulse, and turn on notifications so you never miss the next deep dive. Thanks for watching. See you in the next one.